So, welcome everyone. This is one advantage clear of having the computer in front of you while starting a session is that you have the seconds clearly marked, so we can start on time. We have this session on mesh and modal adaptivity, which has 6 presentations listed here. So as usual, we will start with playing the videos, 5-minute videos from the presenters, and then we'll have the discussion. It's always a pleasure to be with the ADMOS community. It's a pity we are not in Gothenburg, as we were 20 years ago, some of us, probably me and Pedro only. But we start right now with the first presentation by Alexandre Cabousset, an adaptive method for the numerical solution of a 2D Monge-Ampere equation. Alexandre Cabousset comes from the University of Applied Sciences and Arts at Geneva. And so we start with the video, please.
So I present an adaptive method for the numeration of a 2D Monge-Ampere equation. This is joint work with Dimitrios Gozolidis and Marco Picasso from EPFL and funded by the Swiss National Science Foundation. The 2D Monge-Ampere equation is an example of a fully nonlinear equation. Considering here a domain omega in R2, we're looking for a function u such that the determinant of its Hessian is given by data f with boundary conditions. In order to tackle the solution of this problem, we are going to introduce a flow problem, namely the time evolutive problem with the introduction of the time derivative, and we are going to look for the stationary solution of this problem. By noticing that actually the determinant of the Hessian can be rewritten as a nonlinear diffusion, we can actually see that this problem has a flavor of a nonlinear heat equation, where the nonlinearity in green is a cofactor matrix of the Hessian, and we have to make sure that this remains coercive, and that means that the solution we're looking for convex solutions. So in order to tackle this approximation, since the problem is nonlinear and rather stiff, we are going to advocate a midpoint rule for the time-stepping algorithm, which means that at each time step we are going to solve a Newton method, safeguarded, to progress to the next time step. And eventually our goal is to capture the stationary solution. From the space discretization point of view, we are going to introduce adaptive mesh refinement. We are going to work with continuous piecewise linear finite element, and this mesh refinement will be incorporated at some of the time steps. So very classically, we are going to look for the error indicator eta such that the efficiency index is bounded from above and below by a given tolerance. When you look at the weak formulation and its Galerkin approximation, you see that we are going to have to approximate the second derivative of the solution, the approximation UH, and that means that we are going to use mixed finite elements with regularization because we are working with piecewise linear finite element. So technically, we are going to use a residual approach. So the residual here in red will be on one hand bounded from above, very classically by the estimator in blue times the gradient of the error. On the other hand, we are going to bound this same residual in red from below thanks to the smallest eigenvalue of the cofactor matrix. And here we can see that we have an extra term in green that comes from the approximation of the second derivatives. And that will be more difficult to approximate. So when we wrap up everything together, we see that the gradient of the error will be bounded by two terms. The one in blue, that is a classical one, that comes from the residual, and the residual has one point on one part of the residual on each triangle, plus one part composed by the jumps on the internal edges. And the second term in green is this gamma. This comes from the approximation of the second derivative that is theoretically more complicated to estimate. Nevertheless, when you look at some numerical examples, starting with a smooth one, so here where the solution is very smooth, we work on the unit square and we have an exponential function, we can see that all the indicators behave appropriately. Namely, in blue, red, or green, we all have first order convergence for all these indicators here, and error on the second derivatives. Now, when we turn to non-smooth problems, so here we have a solution that has singularities in its gradient in the corner of the unit square. So here you can see that we don't have an optimal behavior anymore because we have a singularity. And actually, we don't have the right convergence order for the H1 norm, but we do have the right convergence order for the L2 norm, as expected. And practically, we can see that the algorithm refines appropriately in the corners of the region. This is where the singularity lies. Finally, an example without an exact classical solution, still on the unit square, and here same conclusion. We see that we don't have an optimal convergence order for the error estimate. Nevertheless, practically, the algorithm refines very appropriately next to the boundary of the square domain, because this is where the problem lies in the solution.
Thank you, Alexandre. Well, you are around, we'll talk in a minute. So the next presentation is by Juan Giraldo. He's coming, I suppose, from down under. So he's from Curtin University in Perth. So he's from Australia. And he has a lecture called An Adaptive Stabilized Finite Element Method Based on Residual Minimization for Unsteady Advection Diffusion Problems. So I ask, please, start the video.
Good morning, everyone. My name is Juan Felipe Giraldo. I am a PhD student of civil engineering at Curtin University. The basic idea of this work is to develop a method for unsteady problems to find for each time step an stabilized discrete solution in a continuous space by minimizing the residual in a discontinuous norm. This residual minimization will help us to get a continuous solution with the good properties of a discontinuous space, such as the in-sub stability from the discontinuous Galerkin method. To illustrate, this is a rotational three-dimensional flow with an inflow boundary condition in the bottom. We start with an initial mesh at time 0, totally independent from the solution. So using the method of lines and solving a saddle point problem from the residual minimization that I will describe later, we obtain a solution in the time n+1 and an error estimator which measures the difference between the discontinuous and the continuous solution. Now with this error estimator, we obtain an adaptive refinement at every discrete level for each time step until we reduce the error in the space until the point that we consider enough. So in this case, for instance, we have 10 levels of refinement from the time step 0 to the time step 1, and then we project this solution to the next time step and repeat this process until finish. For this case, we consider a diffusion advection problem with homogeneous threshold boundary conditions. As a first approach, we aim to approximate the exact solution U of our model problem by using a discontinuous Galerkin method, where the solution lives in a broken polynomial space PH. And for the time discretization, we focus the explanation on backward Euler scheme. Then we can obtain finally a fully discrete method, which can be written in terms of the linear operator B for convenience. By solving a linear problem, we can obtain a discontinuous solution in the time n+1. Additionally, we define the fully discrete energy norm, delta T, which contains the L2 norm and a BH norm from the discontinuous Galerkin. So far, this is only theory of discontinuous Galerkin method. Now we're going to extend the idea of Calvo et al. In 2020 for an steady formulation. The main idea behind the method is to find a continuous solution for each time step in UH, such that UH is a proper subspace of the broken polynomial space PH that we already defined for the discontinuous approximation. What we do now is to find a solution in n+1 in UH such that this solution is the minimum residual in the dual of the fully discrete energy norm of the DG formulation we already defined. What we finally solve in each time step is this saddle point problem, which is the equivalent mixed formulation from the residual minimization problem, where UH n+1 is the continuous solution in the time step n+1, and epsilon in n+1 is our error estimator. This error estimator measures the distance between the discontinuous solution and the continuous solution in the time steps n and n+1. The refinement strategy that we use is to compute a local estimation of the error in the norm delta t in each time step. We mark the elements which have a MOS error, and then we let the software to refine. And we repeat this process in order to reduce the space error in each time step. To illustrate the error estimation of an steady scalar PD, we are going to consider first the heat equation in 2 dimensions. And as a result, we show in black and dot blue line the error of the continuous and the discontinuous solution, measured both in the fully discrete energy norm, and here we can see that we obtain an optimal convergence. And in green and red line, the error of the distance between the continuous and the discontinuous solution, and the error of our estimator, both measures in the delta t norm. This shows us that we obtain a robust convergence in that norm. So what we can also show in the right image that we preserve the first order of the time convergence from our implicit first order time integrator method. In the second example, we show some results of a diffusion advection rotatory Gaussian profile, which move from 0 to pi degrees in clockwise motion. And we clearly see the mesh nodes are concentrated on the place where the solution varies largely, which means that the adaptive algorithm refines efficiently while the problem is moving around the domain, avoiding unnecessary refining. So to conclude, we have a stabilized finite element method based on a stable DG formulation for unsteady problems. We have an error estimates guide adaptivity. We have a method that is simple to implement, and finally we get an optimal convergence in space and time. Thank you so much.
Thank you. So now we come back to Europe. We have a presentation by Ondine Chanon on an a posteriori error estimator for analysis-based defeaturing. And Ondine is coming from EPFL, so in Lausanne. So please.
Hello, my name is Ondine Chanon, and I will pitch our work on the a posteriori estimation of analysis-aware defeaturing. This work has been held at EPFL in Switzerland, together with Annalisa Buffa and Rafael Vasquez. Defeaturing consists in simplifying geometrical models by removing the geometrical features that are considered not relevant for a given simulation. In other words, given a PD and some complex geometry, such as the one on the left, defeaturing consists in removing the features which do not alter the accuracy of the PD solution. In the defeatured geometry on the right, many features have been removed, such as holes, protrusions, fillets, or roundings. By doing so, the computer aided design process is simplified, together with the meshing problem that is otherwise often unfeasible. And it enables faster simulations for engineering analysis problems. Moreover, repeated design changes is a typical process in simulation-based design for manufacturing, and it involves adding or removing geometrical features to the design in order to meet design requirements. We therefore need to accelerate the process of analysis-aware geometric design by defeaturing, and by analysis-aware, I mean that it is very important that we understand the effects of defeaturing on the accuracy of the solution of the problem at hand. This is why in our recent work, we give a solid mathematical framework for analysis-based defeaturing. Moreover, we introduce an a posteriori estimator of the defeaturing error, that is, of the error between the solution on the exact geometry and the solution in the defeatured geometry. We consider Laplace equation on 2D or 3D geometries that contain very general features. They can be negative, such as holes, positive, such as protrusions, or more complex with both positive and negative components. Our estimator is proven to be both reliable and efficient, and its effectivity index is independent from the size of the features and from their number. Moreover, the estimator is easy to compute and very cheap. Indeed, after the computation of the solution in the defeatured domain, it only requires the computation of local boundary integrals and of the solution of a local problem in a simplified features, such as the bounding box of the feature if the feature is a protrusion. The estimator has been tested on an extensive set of numerical experiments. So instead of having to introduce some notations to show you the explicit expression of the estimator, I will show you two numerical examples that demonstrate its efficiency and its capabilities. This first numerical experiment shows that the proposed estimator is not only driven by the geometrical properties of the features such as their size, but also by the solution of the PDE at hand. Indeed, let us consider the geometry containing two holes that is illustrated in the left image. In this case, the defeatured geometry is simply a square. The upper right hole F1 is 2 orders of magnitude larger than the bottom left one, called F2. And the considered Laplace problem gives the exact solution that is shown on the right. This solution has a very high gradient near F1, while it is almost constantly 0 near F2. Therefore, one can expect the presence of F1 to be more important than the presence of F2 with respect to the solution accuracy. And this, even if F1 is notably smaller than F2. We can see in the table that this is indeed the case. E1, the estimator corresponding to the feature F1, is 4 orders of magnitude larger than E2, which is the estimator corresponding to the feature F2. This confirms the fact that our estimator correctly assesses the impact of defeaturing on the solution. It is not only driven by geometrical considerations, but also by the differential problem at hand. Finally, in this second experiment, we consider the geometry on the left that contains 81 holes, and the Laplace problem that gives the exact solution on the right. Let K be the number of features contained in the defeatured geometry. That is, the defeatured geometry will contain the kth first features according to the numbering in the left image. For example, when K equals 8, the defeatured geometry has 8 holes and is as the image on the left. When K equals 59, the defeatured geometry is that one instead. Now for each K, we can compute the value of the estimator and of the defeaturing error, that is the error between the solution on the exact domain containing 81 holes and the solution on the defeatured domain containing only K holes. This allows us to obtain the following graph, where the error is in red and the estimator in blue. We can see that if we allow for an error of 10%, it is enough to compute the solution in the geometry containing around 15 holes. That is less than 1/4 of the total number of holes. If instead we allow for an error of 1%, then we need around 70 holes. We can therefore see that the estimator is able to tell us which and how many features can be removed to simplify the computation and which features should be kept given a certain tolerance on the defeaturing error. For more information and for the mathematical details and proof, you can refer to our recent preprints. Thank you.
Thank you. We have now the presentation from Matthew Hubbard from the University of Nottingham. The presentation is titled Moving Mesh Methods for Implicit Moving Boundary Problems. Please.
My name's Matthew Hubbard, and I want to introduce some work that I've done with 2 students of mine, Tom Radley and Harry Wells at Nottingham, on moving mesh methods for moving boundary problems. In particular, we're just looking at time-dependent partial differential equations of the form that we have here, Quite often these will turn out to be conservation laws, but they don't have to be. We have a situation where the domain is allowed to move in time. There might be internal moving interfaces, and we want to move the computational mesh. The method that we're going to be looking at is one that I helped Mike Baines and Peter Jimak develop a few years ago, a moving mesh finite element method. But in particular here, we're looking at the question as to whether we can achieve higher order accuracy on arbitrary meshes. The underlying idea is simply to set up some sort of conservation principle. So if we think of rho as some sort of density and omega as a test function, we're assigning some mass to each of these test functions. We use Reynolds transport theorem, and that then leads us to a set of equations that we can use in this case to actually try and work out what the mesh velocities are and what the velocity field is that we would allow our mesh to move in. Our omegas are a partition of unity because we're looking at this underlying conservation principle, and we actually assume, as happens in almost all work on moving mesh methods, that the test function moves with the velocity field, which means that this bit that is grayed out disappears from our equations. What we do though is we use this equation to actually find out what the velocity field is. So we replace our velocity by a velocity potential gradient, and then we replace our time derivative of rho with the differential equation. So here the differential equation is determining the mesh movement. We have the freedom to choose what we do with these terms here, and that's relating to the distribution of the points. So we can retain a distribution from an initialization, which might be equidistributed. We recover our velocity from the potential. We have made an assumption in this particular case that the curl of the velocity field is 0, but that's not essential. And this allows us to move the computational mesh. Once we've got this, we can recover the solution values, having moved the mesh using a standard, essentially conservative, arbitrary Lagrangian Eulerian framework, which is what comes out of the, using the Reynolds transport theorem again here and approximating in time. We can use an explicit Runge-Kutta method. The key idea here for high order is that we actually ignore the high order information that we generate for the velocity fields when we're doing the updates here. So we actually only look at nodal positions and how they change rather than anything in the interior of the elements. What this allows us to do is when we apply it to a particular example, here the porous medium equation, then we actually are able to get the higher order accuracy that we might expect. So here we're going up to 4th order polynomials, and we can see that until rounding error starts to interfere, which is at a higher level than it might normally be here, so around about 10 to the minus 11 where these red lines are, we're getting this high order accuracy. Now this is just in one dimension. There is other work going on moving into higher dimensions and also improving these methods, but in particular we moved on from a finite element framework in the Baines and Jimak work. Tom Radley worked on the discontinuous Galerkin approach. Harry Wells has been working on a virtual element approach to look particularly at improving the robustness in higher dimensions. And if I just show finally one result from Harry's work in terms of what we can now do in 2 dimensions with the virtual elements on arbitrary elements, you can see that in this particular case, not only can we get the mesh movement on these polygonal elements, it also allows us to insert nodes in order to get different domains merging when we have these moving meshes. So we can get higher order in 1 dimension, we can do second order, so these results are second order accurate in multiple dimensions on arbitrary meshes, and the work from here is going to be looking at how we can combine those 2.
Thank you. So following, we keep in the UK, and we have a presentation by Edward Munda from the University of Exeter on super elements and flexibility methods exploiting hybrid equilibrium formulations.
Hello, my name is Edward Maunder, and this video is entitled Superelements and Flexibility Methods Exploiting Hybrid Equilibrium Formulations. It is authored by myself in Exeter and Professor Almeida in Lisbon. We have collaborated over some 25 years, including at this Devon vineyard during the preparation of the book published in 2017. The main goal of the present work is to formulate a stable form of hexahedral element in solid mechanics. This was introduced at the last ADMOS conference, but now we give more flesh to the ideas in the simpler context of 2D quadrilateral elements. We define a superelement as a development of macroelements, present some numerical results as a proof of concept, and discuss the option of a flexibility method of analysis. 3D macros are formed from assemblies of tetrahedra defined with internal stress fields and external displacement fields for each face. Assembling into more complex solid elements is intended to remove or control the curse of spurious kinematic modes. The idea is simpler to explain for 2D macros. These start with a triangular element and proceed with macro assemblies sharing a common vertex. A quadrilateral usually contains 4 triangles, but we refine the macro to have 8. As for the 3D hexahedron, this subdivision restricts the spurious modes to local ones, as indicated in the next slide. The local spurious mode is illustrated by the broken curved lines in red for degree 3, and involves a pair of collinear sides as well as the interface VP. Admissible tractions must not excite this mode, i.e. they must do zero work with it. Complete continuity of tractions is a sufficient but not necessary condition, so the semi-continuous tractions illustrated are also admissible. The sufficient condition is now applied via a new entity termed a cover, indicated by the solid red lines around the quadrilateral. 2 roles are associated with it. One is to map continuous tractions, in blue, onto a pair of collinear sides. The second role is to map side displacements, dashed green lines, which are generally discontinuous, onto continuous cover displacements, the solid green line. These dual maps lead to a flexibility matrix G, which transforms cover tractions to cover displacements. A proof of concept concerns the diffusion of tractions applied to a square elastic domain with a fixed base. The model is composed of 4 superelements having stress fields of degree 3. The underlying macros are shown on the right. The number of traction parameters varies from 3 per cover, representing the stress resultants, to 8 per cover, representing a complete basis of degree 3. The errors in total strain energy are tabulated to highlight the effects of varying the degree of the covers. Analyses of the mesh use the flexibility method, which makes direct use of the flexibility matrices G of each superelement. This method only requires very simple definitions of generalized force paths to define a particular static solution, e.g. the green path, or the hyperstatic solutions, e.g. the blue and yellow circuits. The number of hyperstatic solutions can be as small as 6 or as large as 36, depending on the degree of the covers. In closure, the superelement concept has been demonstrated, albeit in 2D, but future work is needed for the hexahedron. This will involve larger dimensions of the stiffness matrix for the macro and the flexibility matrix for the super, dependent on the degree and the number of tetrahedra in a macro. 24 may be needed in order to avoid any bias due to the subdivision. Then there remains the question of how to account for non-planar faces in solid elements. So thank you for your attention. More details are to be found in the extended abstract.
Thank you, Edward. So now we follow to Sorbonne University, a presentation by Lucas Provost, metric-based adaptive mesh refinement and flux error in CFD problems. Please.
Hello, I'm Lucas Prouveau, and today I will present you the work we've done with Anka Belme and Daniel Fuster at Institut Jean-Leron d'Alembert, which belongs to Sorbonne University and CNRS. It deals with metric-based adaptive mesh refinements and flux error in CFD problems. For this work, we use the software Basilisk, which is developed by Popine and which uses finite volume discretization on quad-tree grid structure. It also has its own wavelet-based adaptive mesh refinements implemented. We focus on the diffusion reaction equation, noted by one on the slides, which is solved using a multi-grid iterative Poisson solver. Later in this presentation, we will also use a metric-based isotropic interpolation error, which we newly adapted from the equivalence anisotropic theory from Alose and Losey, and we made this adaptation due to Basilisk grid constraints. To begin with, we start with a small numerical experiment, which is based on the f function which is written on the slide. This function has a particularity to be multiscale with 2 scales in amplitude and 2 scales in wavelength. We made a coarsening study, which means that we begin with a fine Cartesian mesh and we go to a coarser adapted one using exact interpolation error, as we can see on the figures. On these meshes, we were particularly interested in comparing the interpolation error obtained by directly inject the solution at cell centers, which are the green dots, and comparing them with the numerical solution of the solver, which are the blue dots. We clearly see that when we coarsen the grids, the error of the solver becomes significantly larger than the interpolation error, and we can see an error explosion. We've done the same job with the default wavelet-based estimator, and we clearly see that there are similar results. Investigating a bit more about this error explosion, we saw that it depends on the initial grid size, and as we can see on the right plots, which represents mesh levels, which are directly linked to cell sizes, which means that in red you have the smallest cells and in blue the biggest cells. You clearly see that the mesh which have the lowest error is the mesh with the minimal aspect ratio between biggest and smallest cell sizes. We must also say that this error explosion is linked with this test case, which, as far as we know, has not been reported before. So to overcome all of these issues, we imagined a new simple model which must take into account the equation to estimate the error. So to do that, we first estimate an interpolation error using the metric-based error estimator. And then we propagate this error using the discretization of the iterative solver. We also have some IMR control. We stopped when an objective cell number is reached. And we add the constraints on the aspect ratio of minimal to maximal cell sizes. This leads to the following results. So with the blue dots, you have the results with our algorithm, which tends to be close to the theoretical optimal convergence, and you see that there is no more explosion. The results are also better than the wavelet-based results, which are the green dots. And comparing the meshes from the two different methods, we also clearly see that they are different. So finally, we found a new challenging test case for diffusion reaction equation. We also clearly established that there is a distinction between interpolation error-based adaptive mesh refinements, such as the wavelet-based one, and solver error-based adaptive mesh refinements such as our model. We found also a new modelization of the solver approach, which gives good results. Currently, we are studying an incompressible LS solver, which couples an advection step and the Poisson solver used in this presentation. And finally, we want to achieve to do the same with an Navier-Stokes equations and a multiphasic solver. So this concludes my presentation. Thank you for the attention, and if you have any question, please feel free to ask them.
Well, thanks to all the presenters for their videos. I have a series of questions that were asked on the chat room. You can still participate if you want. I will go in the sequence of the presentations. So to Alexandra, there was a question by Alexei Lozinski. How do you take into account the non-exactness of the nonlinear solvers?
Yeah, thank you, Alexei, for the question. Actually, it was a discussion during the work. We don't, as of now. I'm taking that you're asking about the nonlinear Newton method at each step of the time-stepping algorithm. We don't, and this is probably why the error estimate we obtain is not entirely optimal yet. And it was a discussion. We didn't push in that direction because we wanted to go in to see how the algorithm was behaving for non-smooth problem, because a non-smooth problem with singularities were the focus, the target that we wanted to achieve. But that's a good point, and the honest answer is we don't.
Okay. Also, actually, I also have a question. It's not a question. It's more a visual observation. In your example for the non-smooth solution at the corners, I would expect the refinement to be radial around the corners, but it is not. Do you have an explanation?
It is yeah. I don't know what will be my expectation. It has some time of kind of counter-radial type of things. We don't have we don't have a real good answer to that. But this is something we observed consistently also on other problems, on other test cases. At this stage, I would say that we were happy with the fact that it was kind of symmetric already, but that's right.
And it's finding the right spot. That's
and that was and that was the first smile. It's finding the right spot at the right pace. But that's right. There is and we don't pretend this is a work that is finished. Clearly, something more to investigate. I'm not sure that we should have something that is kind of radial in the other way around.
It was just an impression looking at the solution because you have R squared and the square root. So okay.
To be continued.
To be continued. That's correct. So there is a question by Kuyu He for Juan Giraldo. Are you using some FEM package for the demeshing mesh coarsening procedure?
Hi, good night, everyone. Thank you, Kuyu, for the question. So yeah, so far we are not using coarsening, and as a limitation of the package of the FEM package that we are using. So, and that's why we are moving to a DL2 that allow us to do that. So as you expected, yes, we are starting for each time step with the same coarse mesh, and then we project in an L2 an L2 projection to the next time steps. So yeah, of course it's a limitation, but it's something that we are solving.
Okay, thank you. Actually, I also have a question about the effectivity of the estimator that you obtain. You don't have an idea of of the quality.
Yes, so far, so we have robustness convergence with our error estimator. So for the in a space, so we can get a good representation until we get to the error of the time margin. So yeah, but yeah, so far it's something that we expect. Yeah.
Okay, thank you. So for Ondine, there is a question from Pedro Dias. In the examples, you obtain overestimations of the error. Is the estimator providing certified upper bounds?
Hello, can you hear me?
Yes, it's perfect.
Okay. I'm sorry not to turn on the video, but I've been sick all day, so I prefer not to.
Okay, no problem.
But yes, so actually we've proven that the estimator is both reliable and efficient. That is that it's both an upper and a lower bound for the error. And in particular, the effectivity index that we obtained is very low. It's around like 203. And actually, if you look at the paper, we've done also many other tests to really show that the estimator is both the upper and lower bound on the error, in particular the constant in between is independent from the size of the features and from the mesh size. So yes, we've proven that in all cases in which the features are either positive, so like protrusions, or negative, like holes.
Okay. So the question by Jaron Wakers is, how can you know the importance of the different features without solving on the non-defeatured geometry? Actually, that is part of a question I was also thinking about.
Yes,
yes. What is the trick? What is the trick?
Yes, that's actually a good question. But actually, the estimator is built in a more or less similar way as like a residual error estimator for final telemetric approximation, except that now it's on the approximation of the geometry. So basically, it's a variation method. So we, if we think of the easiest case, which is the case in which the geometry has a hole. So suppose that we have a square with a hole in the middle, and the defeated geometry is just the square without the hole. Then the simplified geometry, if we restrict the simplified solution to the exact geometry, so because in this case, the exact geometry is a subset of the simplified geometry. So we can restrict the simplified solution to the exact geometry and then write the weak formulation that it verifies together with the weak formulation of the exact problem, so that we can obtain a weak formulation of the defeaturing error in the exact geometry. I hope I'm clear. And actually,
yes, please.
Yes, so maybe I can share my screen 2 seconds.
Yes, please.
Okay.
If you have the solution at hand,
we
there are more questions in the same direction, and I also have questions in the same direction. So if you can.
Yes, so can you see a slide here? Okay,
yes.
Good. So here I call U the exact solution on the exact geometry omega, which is here. So just the square without this little f, which is the feature. And I call U0 the approximate solution in the defeatured geometry, so in the geometry which would be here just the square. Okay, and if we, so in this case, we consider Laplace equation with Dirichlet and Neumann boundary conditions, but in the feature we impose Neumann boundary conditions. So we can actually write the problem that is verified by U, which is the actual problem that we're interested in. And then we can write the problems that is verified by the restriction of the defeatured solution to the exact geometry. So in particular, it will have some Neumann data here, which is actually the flux of this U0 through this piece of boundary. So in particular, we will have Laplace problem, which has like homogeneous boundary conditions everywhere except on this little piece gamma. which is where we make actually an error. So the whole error, if we want, is concentrated on this piece of boundary that does not exist in the defeatured geometry, but which does exist only on the exact geometry. And in this case, actually, it's possible to rewrite the error as, so in H1 norm, so in the energy norm, as simply an integral on this piece of boundary. And then we will see that this is actually the term that interested us. So G is the Neumann boundary condition on this gamma of the exact problem. And the U0 over dn is the normal derivative of the defeatured solution on this piece gamma. So it's enough to evaluate this normal derivative. And we see that actually this error, which is the error that we make on the normal derivative of the solution on this gamma, is actually what really represents all of our defeaturing error. And then when we write, so there are a few analytic steps to obtain the estimator, which is basically, we can just simplify it, sorry, here. So the estimator will be this one, which is just some weights that tell us the importance of the size of the feature. So it's basically a scaling that gives us what is the correct weights that to give to the estimator for the size of the feature. And then this is actually the part of the error that depends on the problem at hand, so on the differential problem that we have at hand. And here is the error in the normal derivative of the solution on this piece of boundary that is removed by the featuring. I don't know if it helps a little bit.
Well, I think it also answers one question by Juan Rodenas. He was asking, could you explain the basis of the error estimation? So that's, you already more or less answered that question. I was thinking exactly about boundary conditions, but the problems that you solved have non-homogeneous boundary conditions inside. That's the point, yes? Or do you?
No, the problem that we solve is a Laplace equation with any boundary conditions, so not necessarily homogeneous.
Okay, but when you have that smooth solution, the point is, I was thinking about derivatives, fluxes. If you put the lots of holes together, the fluxes will change from the solution with and without, not effects, but well, the inclusions or not, if you put the hole or not. How is that changing? That's
Yes, exactly. Actually, so at the end of the day, what we really observe is that the defeaturing error is really concentrated on those boundaries that appear or disappear because of defeaturing. And then it is enough to look at the fluxes there around to be able to estimate the error.
I think about solids. If you have two holes which are close together, you cannot analyze them independently. Well, but it's something to think about. I think it's, but anyway, it's quite interesting, and I think you'll have people reading your stuff tonight. So that's a good idea.
Yes, actually, the estimator is independent from the closeness of the features, but we can often observe that two features very close to one each other will have a strong influence that we will need either to add them both or remove them both at the same time. This is true.
Actually, there is a new question by Professor Pedro Dias. If you don't account in the estimator for the value of the defeature solutions inside the features, you don't account? That's a question. And then for global quantities like energy, this might be a problem.
So in the case of a negative feature, so like a hole, the only thing that interests us is really the value of the normal derivative by the boundary of the feature. Then in the case of a positive feature, so a protrusion, actually it's a bit more complex because first we need to know how to define the error actually, because what interests us is the energy error in the exact geometry. But in the case of a positive feature, the defeatured solution is not defined everywhere on the exact solution because it will not be defined on the positive.
It doesn't
feature.
exist.
Exactly. So actually there is one more step that is a bit tricky, is that we need to solve a local problem in the positive feature so that we extend the defeatured solution to the positive feature. And then in that case, yes, we'll need to look at the solution in the feature. So we need to look at the extension of the defeatured solution in the positive feature.
Okay.
But still, it will only depend on fluxes there around.
We'll have to look at that. Okay, thank you very much.
You're welcome.
So for Matthew Hubbard, we have a question by QU. Does your mesh degenerate in some areas after moving? How do you deal with that?
Okay, thank you. Yes, very good question. So for more complicated geometries, particularly when the boundary moves in very complicated ways, and particularly when boundaries fold in on themselves, other situations, so Harry Wells did some simulations where we were looking at the interactions of these expanding domains with solid wall features. And when these solid walls had sharp corners in them, moving around those corners also caused issues with the mesh degenerating. And these are typical issues with moving mesh type methods. So the first approach that we use, which will work in some situations, is actually within the same framework. So the moving boundary framework we used here was to use a sort of a conservation of mass principle to move the mesh, but we don't have to use that. We need that to work out how the boundary moves, but once the boundary has moved, we can choose how to move the mesh in the interior. So we can do that by introducing some sort of alternative sort of monitor function within the same framework, or we could just go to a completely different approach for distributing the points in the interior and then working out what velocity that implies. So we can, once we've found the boundary motion, we can use almost whatever we want to do in the interior in order to try to avoid the mesh degeneration and tangling. That is potentially quite expensive. So it's one of these situations where quite possibly in the long run, the most efficient way to do something is, rather than using a pure moving mesh method, to do some remeshing, particularly close to the boundary, which is again a common fix for the issues that come with these types of moving boundary problems. So yes, we do get mesh degeneration. There are ways around it, but for really complicated boundaries, it probably needs to be combined with some sort of remeshing and sort of bench refinement.
Okay, thanks. Makes sense. Thank you very much. So for Edward, there is a question by Pedro. To what extent the macro element concept coincides with the type of solutions used in stars or node-centered patches in flux-free error estimates? Edward, you have to turn on the sound.
Yeah. Can you hear me?
Yes, it's perfect.
Right,
now.
okay. Yeah, the formation of what I call the super element is certainly based on the ideas we've worked on with stars, and because there's a central vertex within the element. So can you repeat the question?
To what extent the macro element concept coincides with the solutions used in the stars or node-centered patches in flux-free error estimates?
Okay, well, it's much the same idea, really.
But, well, I was thinking that you are not doing the overlapping of stars afterwards. You are finding one element only for the star.
The super element is essentially can be viewed like a macro element. It's a discrete block of material. They don't overlap. They simply are adjacent to each other, as normal elements would be. So it's different from that aspect. Yeah.
Okay, thank you. So actually, I have a question for Lucas, because you talk a constraint between ratios, and it appears that when the ratios of the elements are smaller, the solutions are better. This constraint is global or local? Because at the same time, I understand that you have a very steep solution and you want to have a proper meshing, discretization in that region. But if the solution has very different gradients, which change also smoothly, I would expect that this constraint would not be necessary. Can you elaborate on that, please?
Hello.
Yeah.
This constraint is global on the mesh, and it almost depends on the solution. So here for this problem, it is yes. So it's so it depends on the solution, and we almost see that for this particular problem, it helps a lot to make these constraints, and we also made that on several other problems, and which was basically the same idea, but this is we see this problem at most on these particular problems. I don't know if I answer all of your question or not.
Well, it was just an idea of how, if for other solutions you might have different ratios, and it might not be that relevant, or you think it will always be relevant.
Yes, we have made that, and the fact is we have made some procedures to compute automatically this ratio, and so it's not a user input, but it's automatically computed
From the solutions.
Yes.
Okay, thank you. So I think there are no further questions. We are 5 minutes in advance, but anyway, it was an interesting discussion. I want to thank all the participants and all those who asked questions, and also thank all those that are attending for your interest. I hope to see you soon. So just for the information we are now changing, so I need to put this online. Next session, I have this comment that this is not coffee break. I think, looking at the mug, I think it's a tea break, because you have a tea bag in there. Oops, clearly it didn't go well. But so in 15 minutes, we start with the plenary session by Professor Hansbrough. See you soon. Bye-bye.